All right, so get this. Today we're diving deep into material science.
Yeah.
Like seriously deep.
Oh, wow.
You ready to see your pencil and like that diamond ring you might have like in a whole new way?
I'm ready. Hit me.
Okay, so we're going to unpack some excerpts from an IGCSE chemistry study guide.
Sounds intense.
Yeah, it's a little dry. I'm not going to lie, but stick with us. It gets pretty wild once you start like looking into it.
I mean, we are talking about the atomic structure of carbon and metals, right?
Yeah, basically like how those tiny little arrangements actually create the properties of the stuff we use every single day.
It is pretty mind-blowing when you think about it.
Right. So today our mission is to figure out how a lump of coal can basically be the same thing as a diamond.
And why a paperclip bends, but your diamond earrings don't.
Right. That's the part that always gets me. How can a diamond and a lump of coal be like the same element?
It all comes down to something called allotropes.
Allotropes, okay?
Yeah. Basically, it means that the same element can exist in different structural forms.
But different shapes or something.
Kind of. It's more like, think of it like building with Legos. You can use the same blocks to build a castle or a spaceship, right? Same
Yeah.
blocks, totally different results.
Okay, so carbon is like our Lego brick here, right?
Exactly.
So how does it make something as hard as a diamond?
Well, in a diamond, each carbon atom is bonded to 4 others in this super strong, rigid structure. It's called a tetrahedron.
My tetrahedron.
Yeah, it's a very specific shape. But basically, it creates this tightly packed 3D network. And that's why diamonds are so hard and have a crazy high melting point. Like, you need a ton of energy to break all those bonds.
Yeah, which is why they use them for industrial cutting tools, right?
Exactly. They can withstand insane temperatures and pressure.
That makes sense. But what about graphite?
Ah, graphite.
It's like soft and slippery, right? Basically the opposite of a diamond. So how does that even work if they're both just carbon?
Well, that's where things get really interesting. So in graphite, each carbon atom is only bonded to 3 other carbon atoms. And this creates these layers of hexagons. But the layers are only weakly bonded to each other, so they can easily slide around.
Oh, so that's why graphite is used in tensile.
Exactly. As you write, those layers just flake off onto the paper.
That's pretty cool. But wait, didn't you also say that graphite can conduct electricity?
I did.
But a diamond can't. So how does that happen if it's still just carbon?
Okay, so remember how I said each carbon atom in graphite is only bonded to 3 others?
Yeah.
Well, that leaves 1 electron from each carbon atom free to roam around.
Okay.
And those free electrons can carry an electrical current.
So they're just like zipping around in there.
Pretty much.
But then why doesn't the whole graphite structure just fall apart?
Because the bonds between the carbon atoms within each layer are still strong. It's just the bonds between the layers that are weak.
Gotcha. So it's like strong in one direction but weak in the other?
Exactly. And this is a great example of how a seemingly small difference in atomic structure can have a huge effect on a material's properties. And that, in turn, changes how we use it.
That makes a lot of sense. So both diamond and graphite are examples of what's called giant covalent structures, right?
They are.
That sounds kind of scary.
It's not too bad, basically. It just means a massive network of atoms, all linked by strong covalent bonds.
So both diamond and graphite fit that description, even though their properties are so different?
Exactly.
So they both have high melting points because of this giant interconnected structure?
Right. It takes a lot of energy to break all those bonds.
Okay, I think I'm starting to get it. So structure really does dictate properties, but what about metals?
Metals.
They're strong, shiny, bendable, great conductors. They've got to have their own thing going on, right?
They do. Metals have their own unique bonding system, and it's what makes them so important to our everyday lives.
Okay, so what's the secret? What makes metals so special at the atomic level?
That's where metallic bonding comes in, and that's what we're going to explore next.
Okay, bring it on. I'm ready to dive into the world of metallic bonding.
Buckle up. It's going to be a wild ride.
All right, so we've seen how carbon can be like super strong and also surprisingly slippery.
Yeah, it's all thanks to how those atoms are arranged.
Right, but what about metals? They've got like a whole other set of superpowers.
Exactly. Metals have their own unique bonding system.
Okay, so spill the beans. What makes metals so special?
Well, in metals, the atoms don't hold on to their outer electrons very tightly.
So they're just like letting them go.
Kinda. They essentially donate those electrons to a common pool.
A common pool? Like what does that even mean?
It creates a sea of electrons that flows freely throughout the entire metal structure.
A sea of electrons. Okay, now I'm really picturing this like some kind of underwater rave.
It's a wild visual for sure.
But what holds the metal together then if the atoms are giving up their electrons?
Well, what we're left with are positively charged metal ions.
Okay.
And it's the attraction between those ions and the sea of negative electrons that creates the metallic bond.
So it's like a constant push and pull.
Exactly.
Yeah.
It's a strong bond, but it's also flexible.
Okay, so it's like all the metal atoms are chipping in to create this electron pool that glues everything together.
That's a great way to put it. And this unique bonding structure is what gives metals their characteristic properties.
Like what?
Well, for example, remember how diamond gets its strength from those super strong covalent bonds?
Yeah, they're hard to break.
Exactly. Well, metals have high melting points for a similar reason.
Because the bonds are strong.
Exactly. The attraction between those positive ions and the electron C is really strong. So it takes a lot of energy to pull them apart.
That makes sense. What about electrical conductivity, though? Metals are like the best conductors out there.
Right. Well, that's where those free-flowing electrons really come into play.
Okay.
They can easily carry an electrical current through the metal, like tiny couriers zipping along a highway.
So without those free electrons, our gadgets wouldn't even work.
Nope. No more smartphones or laptops.
Okay, that's pretty crucial. So strong bonds explain the high melting point free electrons, explain conductivity. What about malleability?
Ah, yes. Malleability.
Metals can be bent and shaped without shattering. How is that even possible?
Think of it like layers of marbles. Those positively charged metal ions can slide past each other when a force is applied.
Okay.
So if you're hammering a piece of metal, you're essentially pushing those layers around.
Like a microscopic mosh pit.
And the sea of electrons acts like a lubricant, allowing the layers to move without breaking the bonds.
So the electrons are not only carrying charge, they're also acting like tiny ball bearings.
That's pretty incredible, right?
It really is. It's like starting to click for me now how those tiny atomic interactions create the properties we see and use every day.
It all comes down to understanding the atomic level.
But I have to ask, are there any like real world examples that really bring this to life?
Oh, absolutely. Tons. Let's start with diamonds. Remember those ultra-precise surgical tools?
No.
They use diamond blades because nothing else can hold an edge that fine.
So we're talking about the same stuff that cuts through rock being used for delicate surgery.
It all comes down to diamonds' incredibly strong covalent bonds.
My mind is officially blown.
Yeah.
What about graphite besides pencils? I mean,
Well, graphite is actually used as an industrial lubricant.
a lubricant.
Yeah, think about machinery with moving parts that constantly rub against each other.
Oh, okay.
You need something to reduce friction and prevent wear and tear. Graphite, with its slippery layers, is perfect for that.
So it's like nature's WD-40.
Exactly. And then there's graphite's electrical conductivity.
Right, you mentioned that before. Where does that come into play?
Graphite is used in electrodes for batteries and in some types of electrical motors.
Really?
Yeah, those free electrons allow it to carry the electrical current needed to power those devices.
So the same material that lets us doodle on paper can also help power our world.
It's all about understanding those atomic level interactions.
Hmm.
But what about metals? We've talked about their properties, but how does that translate into real-world applications?
Yeah, give me some examples where those metallic bonds really shine. All right, so we've seen how the unique bonding in metals makes them like super strong and conductive and bendy, but what about like real-world examples? Where do those properties like actually matter?
Well, think about like bridges and skyscrapers. They're built using metals like iron and steel.
Oh, yeah. Okay.
And those metals can withstand like crazy stress and heat.
Yeah, for sure.
That strength and durability are like essential for safety. We don't want our buildings collapsing, do we?
Definitely not. Okay, but those are kind of obvious examples. What about conductivity? We're surrounded by electronics. Where do metals fit into all that?
Think about all the wires and circuits inside your gadgets.
Okay.
Metals like copper and aluminum are the unsung heroes there, acting like superhighways for electrons.
Really?
They allow electricity to flow freely, powering everything from your smartphone to your refrigerator.
Wow, so without those tiny electrons zipping around thanks to metallic bonding, our modern world would just like stop.
Pretty much.
It's amazing how something so small can have such a huge impact.
It really is. And then there's malleability.
Right.
Think about all the objects we create by bending and shaping metals, cars, airplanes, even cookware and jewelry.
Oh, yeah.
That ability to mold metals without shattering them is what allows us to create such intricate designs.
You're right. I hadn't even considered jewelry. The fact that we can take like a hard metal like gold and turn it into a delicate earring or a complex watch mechanism is pretty mind-blowing.
It all comes back to understanding those atomic level interactions.
For sure. But here's something I've always wondered about. Are we like limited to just the materials nature provides, or can we actually create new materials?
That's a great question. And the answer is we can actually create new materials with specific properties by manipulating those atomic arrangements.
Whoa, hold on. So we can like engineer materials to suit our needs? How does that even work?
One way is by creating alloys.
Alloys, okay.
An alloy is basically a mixture of different metals.
Mm.
By combining different metals in specific proportions, we can enhance certain properties.
So like mix and match.
Exact. For example, stainless steel is an alloy of iron, chromium, and nickel.
Oh, okay.
Adding chromium creates a protective layer that makes it resistant to rust.
So that's why we use stainless steel for things like kitchen sinks and surgical instruments. It's durable and hygienic.
Exactly.
That's pretty cool. So we're not just like passive observers of nature, we're active participants. We're using our knowledge of atoms and bonding to create materials that meet our needs.
Precisely. And that brings us to our final thought. For you to ponder as you go about your day, take a moment to look around and consider the materials you encounter, from the chair you're sitting on to the screen you're looking at.
It's like seeing the world through a secret scientific lens.
We hope this deep dive has inspired you to look at the world around you with a fresh perspective. You might be surprised by how much wonder you find hidden in the everyday materials we often take for granted.
Until next time, stay curious,